Welcome. In this topic, what we're going to review is about energy. So, in this chapter, or in this material, the things that we are going to talk about mainly it's going to be energy. But there are also other items that we may also revise, such as power. Okay. So the first thing is like and then of course work. First, what is energy? Energy is the ability to do work. Okay. Then now, what is the definition of work in physics? Work is like, it's not as a simple definition. If you sit the whole day and then front of your computer and then doing your homework, listening to videos and so on and so forth, that's not work. According to the definition of work, then work is defined as, mostly in physics, defined as like work done is equivalent to certain force must be applied and a certain distance must be covered. Okay, and this equation only works if and only if the direction of the force and displacement, those are magnitudes by the way, and displacement are the same, or the same direction. Okay, otherwise it's not going to be applicable. So there is a like, so but what that means, like if you have a block of mass m, and then if you are applying certain amount of force, and then if you drag this object by distance of delta x to this location, then the amount of work done that you have done is equivalent to force times that force multiplied by the displacement, both magnitudes. Okay, now the question is like, what if the force is being applied at a certain angle, theta, and you drag the object a distance of delta x? In this case, then work done is going to be the magnitude of the force multiplied by the magnitude of the displacement and then the cosine of the angle. Okay, so keep in mind. Now this is what work is, but sometimes, like, probably you might be curious, like for instance, if I carry a bucket of water, or let's say your backpack, like you're holding your handbag or backpack or a bucket of water, and you're holding it like this while you're walking in this direction, delta x. Your force is being applied like this. So the amount of work done in this particular case is going to be 0, because the magnitude of the force multiplied by the magnitude of the displacement, you multiply that by cosine of the angle, but your angle right now here is 90, because the force in delta x make 90 degrees. Cosine of 90 is 0. Then as a result, like, your work done is going to be 0. So by carrying a certain stuff, don't assume that like you are doing some work in physics. That's not going to work that way. So the unit of work done is so unit, it's SI unit of work done is Newton meter, right? Because it's the same as the SI unit of force multiplied by the SI unit of delta x, which is displacement, and that has a special name known as joule, and it's represented by capital letter J. Okay, then now let's go ahead and then try to see like energy. There are different kinds of energy, but in this particular material we're going to focus on two different types of energy. So the first one is known as kinetic energy. Okay, so the kinetic energy of an object is the energy by virtue of its motion. So if you have an object that is traveling at a certain distance, then it has a kinetic energy equivalent to half of the mass multiplied by its velocity square. And work and energy, they are scalar quantities. Okay, so that means direction is not that much significant. Of course, work can be negative because work done by friction force is negative. Okay, so keep that in mind. The other type of energy that we will consider a lot more is known as potential energy. This potential energy is gravitational potential energy. Okay, and that potential energy is like, let's say this is the surface of the earth, or the floor. Then if you lift a certain book to a certain height, right, from a certain height, and if you drop this book, like, it can do some work. The work can be like damaging the floor, or maybe hitting the head of a nail or something like that, but still it has an ability to do work. And that kind of energy is known as potential energy, gravitational potential energy. And mathematically it's equivalent to mass times gravity times height. The height. Okay, so like work done, the SI unit of energy is joule too. Okay. All right. So what are the other materials that we're going to go through this particular chapter is the conservation of energy. So the conservation of energy is like, for instance, energy is neither created nor destroyed, but it can be transferred or transformed from one version to another version of it. So for instance, if you take a pendulum, right? So in a very unideal world kind of pendulum. So if you have the pendulum and let's say, then you have the pendulum and then you let it swing. Okay, so this pendulum, what's going to happen is like it's going to come to the bottom, and then it's going to go back to this side, and then it's going to swing like back and forth pretty much forever. If there's no any kind of friction or any kind of air resistance, it's going to go swing back and forth pretty much forever. So literally what's happening is, like, if you consider this, and the pendulum has a potential energy here, okay, and then when it reaches here, if this is your reference level, then its potential energy will be 0, and at this point its kinetic energy is 0 because it stopped for a moment before it starts to swing back. But its kinetic energy is not 0, and it's to a maximum. And then when it reaches here, when it comes back here, then it has a potential energy, but its kinetic energy is 0. So it's going to swing like so, from potential to kinetic, from kinetic to potential, and then back and forth, and then that procedure or that motion is going to continue like that. Okay. So in general, the conservation of mechanical energy, we call it mechanical energy. Okay. So the conservation of mechanical energy states that, like, mechanical energy remains constant, okay, in a system. What is mechanical energy? Mechanical energy is the sum of potential energy. So potential energy at a certain initial time plus the kinetic energy at a certain initial time equals the potential energy at a certain final time plus the kinetic energy at certain final time. Okay, so this is what conservation of energy is. Of course, we are not considering, like, in the absence of friction and so on and so forth. There can be like other terms that we need to add, but otherwise, like, this is what the conservation of mechanical energy is. So that means, in other words, half times mass, or let's start with the potential. So it's like potential energy means mass times gravity times a certain height initial plus half times mass times v initial squared equals m gravity h final plus half times v final squared. So this is what the conservation of mechanical energy equation looks like. So what are the other things, or other items that probably that interest us in this chapter. So we say energy is conserved, like whether it's mechanical energy in a pendulum, or if you try to swing yourself in on a roller coaster or something like that. So the amount of swing that you can achieve, like for instance, if you are on a roller skater, if you are like that, and then you are moving, and there is a maximum height that you can reach. Okay, so that maximum height, so here what you have is relatively you have kinetic energy. Okay, so if this is your reference height, at this point you lost all your kinetic energy. That's the maximum height. What you have is your potential energy. So your kinetic energy when you start at this point and your potential energy when you reach here, they are both equal. Okay, at intermediate point you have both kinetic and potential energies. Okay, so the other item is spring potential energy. So what is a spring potential energy? Spring potential energy is, so for instance, like when you compress a spring and you let it go, right? Spring potential energy. So you have a spring, you compress it, okay, by X amount. When you compress the spring and when you let it go, like it recoils or it kicks back, right? So as a result, then it can do some kind of work. Like for instance, if you attach a small mass to the spring and then you let go, then automatically the mass will be launched in this direction, right? So what happens is, like, if the mass is launched in this direction, then the mass gained certain kind of kinetic energy. So according to conservation of energy, then the total mechanical energy is conserved. Total mechanical energy, but what you had here wasn't really a direct gravitational potential energy, but you had a spring potential energy. And as a result, then there is a spring potential energy, and it's defined as half times k times x squared. Okay, where k is spring stiffness, or we call it Hooke's constant or spring constant. Okay, and x is deformation, by how much you deformed the spring. Okay, so that's what the spring potential energy is. So if your conservation of energy involves a spring, then of course you are going to add a term for the above equation that we saw, a kinetic energy term to, a spring potential energy term to it. Okay, so the last item probably in this topic that we are going to encounter is known as power. Okay, what is power? Power is the rate of work done. Okay, how fast you can do a certain work. So for instance, if a certain guy is strong, probably he can carry 100 newtons of, or 100 kilogram of mass, and he can carry upstairs like 5 flights in, let's say, in 2 minutes. Another guy may do the same job in 5 minutes. So who's more powerful? The first person. Why? Because he was able to do the work faster than the other one. So the result, power is defined as the rate of work done over time. Okay, so mathematically power is work done over time. So the SI unit of power unit is joule per second, has special name known as watt, WATT, or capital W. Okay, don't get confused with watt, the W for the force and W for watt. Watt is unit, so usually it comes after a number. Okay, whereas W, work done, it's a variable, it's a physical quantity. It comes only it comes like inside an equation. Okay. So after having said that, then that's pretty much everything that you will encounter in this chapter. So let's go ahead and then probably try to do some examples. Okay, The first example that you see here, it states the unit of work, joule, is dimensionally the same as what? Already mentioned this one, and it is the same as Newton meter. Okay. Second example states a worker pushes a slate. So you have a slate, let's say it's a slate. Force of 40 Newton is applied by the person, but however there is a frictional force which is 24 Newton. This is the frictional force, this is the force that is applied. And then the slate traveled 6 meters from here to here. So that's your delta x, which is 6 meters. Now the question is the net work done. Net work done is just literally, you know, all the net force multiplied by delta x, because in this particular case the forces are parallel to the displacement, so therefore, you know, you can just simply multiply the two. But the net force is you have two forces. One is acting in the positive x direction, then it remains positive, whereas the other force is acting in the negative direction, so therefore it becomes a minus. Then you multiply that by delta x, which is 6. So what you will have is like 16 times 6, which is 96 joules. So that's what the net force, the net work done on the slate is. Second question states, the third probably, which of the following is that form of energy associated with the object's motion? So motion, it is kinetic energy. Okay. Then the following question asks, like, what is the kinetic energy of a certain mass of object, which is 135 gram, which has a velocity or speed of 40 meters per second. And then kinetic energy equals what? So what we know is kinetic energy of an object by virtue of its motion is half mv squared. So, but the question is, like, the mass wasn't given in SI units, so you need to convert that to kilogram. So therefore it has to be 0.135 kilogram. That's what you have to put into your equation. So therefore kinetic energy will be half times 0.135 multiplied by 40 squared. If you substitute everything in the right way, then your answer is going to be 108 joules. Okay. Now, this question asks us if both mass and velocity of a ball are tripled, the kinetic energy is increased by what factor? So you can start like this. Kinetic energy equals half times mass times v squared. Okay, initially. Then the final is going to be like half times, triple the mass. So that means you'll have 3m, and then triple the velocity, you'll have 3v squared. So this will be half times 3m times 9v squared. So your KEF is going to be equal to 27 times half mv squared. If you compare this mv squared and this mv squared, they are pretty much the same thing. The only factor that you have between them is 27. So therefore the energy will increase by amount of 27. Okay. Now, this problem asks you to find a baseball outfielder throws a baseball of mass. So the mass is given. So mass is 0.15 kilogram. The speed v equals 40 meters per second. That's the initial. But there is theta, which is at 30 degrees. Okay. What is the kinetic energy of the baseball at the highest point of the trajectory? So kinetic energy equals what? So the ball is thrown like this. So normally what's going to happen is, like as we saw it in projectile motion, it will follow a projectile. But the thing is, the velocity has both initial in the x, right, Vax, and the initial in the y. Okay, Vx is the cosine component, which is Vi cosine of angle theta. This one is Vi sine of angle theta. So Vix will be V initial, which is 40, cosine of 30 degrees. Okay, then V initial x is going to be that much. So 40 cosine of, I use still my calculator, is equivalent to 34.6 meter per second. So now, as we saw already in the in projectile motion, when an object travels in the x direction or in a projectile motion, what happens is Vix remains constant. So the same Vix will travel everywhere. So at the highest point, Vi, or not Vi rather, Vy is 0. There is no velocity, because at that point what happens is, like, the object starts to come down. There is no velocity in the y direction. So there is the only velocity that you have is Vx, but that Vx is equivalent to Vix, because the motion along the x direction is, it's a uniform motion for a projectile motion. So that is really that what you have to do is just simply apply the kinetic equation, kinetic energy equation, half mv squared, which is half times the mass of the ball is 0.15, and the velocity, the only velocity that you have at the top is 34.6 squared. Okay, so try to simplify this and see what you're going to get. So half times the mass is 0.15, multiply that by 34.6 squared, then the answer is approximately 90. Okay, so if there's choice number 3 is the answer. So this one, it asks you to solve a problem in your textbook, number 36. I'm using like 10th edition of college physics by Thurway. So I'll try to have a sketch. So the problem states like there's something that looks like this somehow, and there is something like a ground, and then there is a small mass m, then it's released from this height, and this height is the initial height, which is 5 meters. And then the ball passes through different points. Like this is point B, which is 3.2 meters high. And there's point C somehow, which is 2 meters high. Okay. So now the question states like a block of mass m released from rest. So that means right at this point V initial equals 0. Okay, so that means there is no kinetic energy over there, and then it's frictionless. Determine A, the block's speed at point B and point C. So problem A asks what is V at B and V at C. So you can proceed in any way you want, but the question is like the conservation of energy. So mechanical energy at point A equals mechanical energy at point B, as far as there is no friction, mechanical energy at point C. So mechanical energy at point A is half times the mass of the object times the velocity at A squared plus m times g times h at point A equals half times mass times V at B squared plus m times g times h at b. Okay, but at point A velocity is 0, then as a result there is nothing. So you have mass m, gravity 9.8, h at point A, which is 5, equals half times mass VB squared, you don't know VB, plus m, also the mass is given, which is a 5 kilogram, but we might not need it. G is 9.8 again. Then h at point B is 3.2 meters. So m is common, then on both sides of the equation you can eliminate them. Then now I'm going to bring this to the other side, then it will be minus automatically, right? So as a result, what you will have is 9.8 into 5 minus 3.2. It took the 3.2 to the other side and took 9.8 as common. Then you have that half VB squared. Okay, so now what you will have is like 9.8 multiplied by 5 minus 3.8 is 9.8 times 5 minus 1.8 equals m is eliminated already, half times VB squared. So 9 times 1.8, 9.8 times 1.8, and then you take 2 to the other side, will be -2, then you'll have 35.28 equals VB squared. Then to find VB, then you have to put this number under square root. Then as a result, B will be approximately 5.94 meters per second. Okay, so once you know how to find for VB, then you can go ahead and then find like for velocity at point C. You can apply same equation, but I can give you the answer. Probably the answer is approximately 7.6 meters per second. Okay, so try to verify that number is correct. So yeah, that's what the question is. And part B, it asks you like what is the net work done by gravity from point A to point C. That one you can find like the net work done by only gravity can be found like, you know, potential energy at point A minus the potential energy at point C. Okay, because work done is the ability to do work, then you know, mostly like when you change like find the change in potential energy, then that indirectly gives you what the amount of work done is. So there is mass, the mass is 5, gravity 9.8, height at A5 minus 5 times 9.8 multiplied by at point C. At point C the height is 2. Okay, so if you simplify this, what you're going to get is 5 times 9.8, approximately 147 joules. Okay, following problems, yeah, it asks for, it's a Hooke's law or spring that obeys Hooke's law is compressed. So now the question says it's compressed from equilibrium, so you have delta x for, so your given parameters as always 12 centimeter, so which is 0.12 meter. And the potential energy stored is now potential energy for this scenario is 72 joules. Okay. So in other words, what is given is like, of course, it's a spring. So potential energy of the spring, which is 72, equals half times k times x squared. So that means 72 equals half times k. You don't know k. Okay. Multiplied by x squared, which is 0.12 squared. So take to the other side. So then, or multiply both sides by 2. Then the 2 cancels out. Here you will have 144 equals k times, if you square this, you will have 0.0144. Okay. Then the value of k is going to be 144 divided by 0.0144. So likely that will give you 10,000, I think. 144 divided by 0.0144 is 10,000 Newton per meter. That Newton, yeah. So now what you need to find is like, what if now the potential energy is 100 joules, then now x would be how much? So the way you will proceed is like, again, potential energy is half times kx squared. K is a constant for the spring. For one spring, you can only have one K value. It doesn't vary from problem to problem. Why? Because it's the stiffness. It measures the stiffness of the spring, how smooth or how soft or how strong the spring is. So now it's just simply a matter of substitution. So you have 100 equals half times K, which is 10,000, multiplied by x squared. So multiply both sides by 2 and divide them by 10,000 to isolate for x squared. So 2, but divide that by 10,000. So this cancels out by this, this cancels out by this. Then you'll have x squared is equal to 200 divided by 10,000, right? So you'll have 0.02. Then x will be the square root of 0.02. Then the square root of 0.02 is approximately 0.14 meters. Then x is equivalent to 14 centimeter. Okay. So the closest is this. So the following number, the problem states a jet engine. So jet engine has certain average force, which is equivalent to 1 times 10 to the power 5 Newton of thrust, moving an airplane forward at a speed of, so, well, the speed is 900 kilometers per hour. What is the power developed or delivered to the engine? Now, we already mentioned that like power equals work done over time, if you remember. So, but at the same time, we define work done is force times delta x over time. But from your kinematics, what we know is like delta x, which is displacement divided by time, is velocity or speed. So as a result, you will have force times v. It's a new equation for you. You can find power if you multiply velocity by force. So the force is given. A jet engine develops like of moving an airplane forward at a speed of that much. What is the power developed by the engine? So what you will need to do in this particular problem is like just simply you need to have you need to convert the velocity to meters per second. So velocity has to be converted to meter per second. You multiply it by 1000, you divide by 3600, because for every hour you have 3600. Then if you do that, what you'll get is 900 times 1000 divided by 3600. Make sure that, like, you use your calculator sometimes. It's fine. There's nothing wrong with using your calculator as far as you understand the concepts. So V is that much. So then simply power will be the amount of forces given, which is 1 times 10 to the power of 5, multiply that by 250, then as a result you will have 25 times 10 to the power of 6 watt. That is equivalent to 25 megawatt. So choice number 3 is the answer. So this is also a power problem. So mass is given. The mass of the object is 1000 kilogram, sports car. Accelerates from 0, that means it has an initial velocity equivalent to 25 meters per second. In 0, 0, 0, 0, sorry. Then it has a final velocity too, which is 25 meters per second. Now the question is, what is the average force delivered? And time is given, which is 7.5 seconds. Aha! So how are we going to approach this problem? We know that, like, power equals work done divided by time. But the work energy theorem also states that work done is equivalent to the change in kinetic energy. Okay, so work energy theorem or kinetic energy theorem states like power or work done is equivalent to the change in kinetic energy. This is W. Then I'm going to use that equation. So therefore power is going to be change in kinetic energy. So I'm just bringing this guy to here. Changing means kinetic energy final minus kinetic energy initial divided by time. Okay. So what is kinetic energy final? That's half mv final squared minus half mv initial squared. Divide that by time. Now the result, what you will have is power equals half times mass of the car is 1000. Its final velocity that it achieved was 25 squared minus half times mass times the initial, which is 0. Then divide that by time, which is 7.5. Okay. Then your power can be found just by simplifying the given problem, which is 1000 multiplied by 25 squared divided by 2 divided by 7.5. Then as a result, like, your answer is approximately 41,667 watt. Okay. So if there's a multiple choice that shows that much, then you go for it. Yep, there it is. Here you are. Okay. So now there are a couple of more problems. So the unit of power watt is dimensionally the same as we already said it. Watt is the unit, not the work done equation. What is the same as dimensional is the same as joule per second. Okay, so joule per second. Number 2, or probably I don't know what number we are in. So there's a power given. Power is given 100 watt. As I said, if W comes right after number, then automatically you should understand that it means it is watt, okay, not work. Then time is 10 hours. Over this period, how much energy? That's pretty straightforward. Energy consumed is how much? So energy, the form of heat or something like that, or in terms of light, the amount of energy consumed by the bulb is the same as the amount of work done on the bulb. Okay, so work done, in other words, equivalent to the amount of energy consumed, can be found by just applying power multiplied by time. Why? We already defined power is work done over time. Then as a result, work will be equal to power times time. Okay, so therefore then your W will be 100 watt multiplied by 10 hours. But in the previous problem, what we said is like work done or energy or power is the same as, you know, joule over a second. So therefore we need to convert the time into seconds. In every hour you have 3600 seconds. We did several examples, something similar to this, so we don't need to really go back to that kind of calculation. Then as a result, if you do this, you will have 36 and then 3 more zeros and joule, and that's what your answer will be. Okay. Actually, how many zeros? 1, 2, 3. Actually, 3, 4, 5. 1, 2, 5 zeros. Okay, which is 3.6 megajoule. Okay. So that's choice number 3. All right. So with this we conclude the chapter. Okay. So